Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, we're delighted to have othersGÇÖ from MIT, and she's going to tell us about opinion dynamics and influence in social networks.
Thank you very much, Madhu. Thanks also for the invitation. It's a pleasure to be back here after quite a bit of time. As Madhu said, I'm going to be talking about our recent work on models of opinion dynamics and influence in social networks. Just as a brief motivation, almost all important social decisions are taken by individuals on the basis of their opinions, and these opinions are formed and updated as a function of the experiences of these individuals, but also the information they receive from their social circles. And this makes opinion dynamics crucial in social and economic networks, or networked environments especially. And a few examples that I've just picked for such dynamics is formation of political opinions, learning about product quality, which is very relevant in the context of marketing, information aggregation in financial and economic networks, and also even intentions in more conflict situations. And if you think about what are the factors in formation of these, as well as evolution of these opinions, prominent agents turn out to be an important factor. And by prominent agents, loosely I mean individuals who have different social standing in the society. So because of this, their social status or resources available to them, or more explicitly because of their explicit intent to influence the opinions, these have a disproportionate impact on the opinion dynamics.
These are prominent not by virtue of their position in the network, but by virtue of some other attribute. Exactly. Because I mean, because of their type, let's say, not coming from the from their position in the network. And by type, I'm essentially here modeling. Think about this as community or religious leaders, maybe political parties, news or media sources, and so on. So this talk will be about models of opinion dynamics in the presence of prominent agents. More formally, prominent agents, the way we define them in our models, will be agents who influence others' opinions, but who have or are subject to more limited input from others. And the talk will have two parts, or essentially two papers. In the first part, we're going to assume that the prominent agents are part of the society in the sense that even infrequently they receive some information from others. So they represent leadership roles, but still listen to the rest of the group. And this is joint work with Darun and a student of mine, Ali Parendegebi from Leeds. The second part will be we're going to drop some assumptions that we're doing here, and it will be about the case when these agents are fully stubborn. And here the goal is to model basically extreme groups, so those agents whose agenda is explicitly to influence opinions of the leaders. Who are you modeling in the first case, and who are you? Nothing.
Okay, so in the second case, so this is actually more recent work. This is joint with Giacomo Como, who was a postdoctoral associate in Leeds. Now he's on the faculty of Lund. And Fabio Fagnani from Department of Mathematics from Politecnico di Torino. So in both of these models, the key questions that we're interested in are, will opinions converge to a consensus? Will they fluctuate? How can we characterize this as a function of the network properties or location of the prominent agents within the network? How much will prominent agents be able to manipulate opinions? And we're going to try to essentially attempt to quantify their impact as a function of some relevant properties of these complex network structures. More generally, I think this is a question of interest. What types of societies and social structures are more robust to manipulation. So this also has a broader agenda, which I will sort of touch upon at the end of the talk, which is actually joint work with Amin. Basically, what can be done from a design perspective to make societies more robust, or opinions less subject to manipulation. So such an analysis will hopefully give some answers that we can use in the context of such design questions. So let me briefly talk about the approach we're taking in both of these models. We're going to model the society as a collection of agents situated in a social network, connecting with a sparse neighborhood of individuals. I will from time to time be referring to learning as a performance metric, and that will be loosely forming correct beliefs about some underlying state. So this state can represent the social question or issue of interest. So since we focus on the impact of prominent agents, we're going to adopt a non-Bayesian framework where some agents can influence others. So that actually raises the question, especially for economists, why not adopt the Bayesian learning framework in the sense of agents optimally processing the information that is available to them. So with
You'll tell us more specifically what
definitely,
it is later?
Definitely. For now, I'm just trying to sort of, develop the framework slowly. So why are we assuming, not assuming Bayesian agents, for instance? Now, with Bayesian learning, the influence on an agent will depend on that agent's belief about whether the other person is trying to influence him or not. So, I'll be able to infer from our ongoing interactions whether Madhu is an agent who is exchanging information or who has an explicit agenda of influencing me. So Bayesian agents will be able to adjust the weights given to Madhu appropriately so that his influence on my opinion gradually decreases in time. Actually, we have some previous work on this Bayesian learning with both Ilan and Kostas. And in those works, as part of those works, we showed that asymptotic learning, in that sense, will not be disrupted if you have a finite number of agents with that particular agenda. The problem with such models, especially on complex graphs, is that these involve complex inferences as well as stringent rationality assumptions, and they will essentially limit the extent of misinformation. So in the interest of sort of highlighting the effect of the underlying graph structure, we will adopt the non-Bayesian framework and view that as a worst-case impact or worst-case characterization of influence in a society. So here is slowly, I'm coming to Madhu's question. We're going to focus on non-Bayesian or rule of thumb learning. Basically, think about interactions rules which are rule of thumb, in the sense reasonable, but not necessarily optimal. So our model will involve a stochastic gossip model of opinion dynamics. And the main assumption will be, basically, we'll consider a society consisting of two types of agents. Regular agents who exchange information, they don't have a particular agenda, and prominent agents. So agents will be randomly matched according to an arbitrary communication matrix P. So Pij, each of the entries will be the probability that I meets J. And we will essentially consider two different interactions happening according to whether the agent is regular or prominent. When I meets J, if J is a regular agent, then meeting essentially will amount to exchange of information. And we're going to model that as each of them, well, they will agree with some probability, and in that case, they will take an average of their current beliefs. So they will update their belief to be the average of their current beliefs. Okay? So essentially, that will represent some form of exchange of information and agreeing in the middle. Okay? And if J is a forceful agent, on the other hand, then meeting will amount to I being influenced by J. And in that case, I will essentially inherit most of J's belief. I will just put some epsilon on his own belief for technical reasons, but that's not even needed really in the analysis.
J never shifts.
J doesn't shift. But there's a caveat, which I will come in a second.
Belief itself is some just real number?
That's what I will assume.
Wait, I don't. You said you have two models, one in which the
This is the first model. Basically, this will be the first model. So let me clarify.
He's forceful but not stubborn?
So in the first one, J, that's actually very related to Jennifer's question.
J never shifts when I communicate with J. But in the first model, I will assume that at certain instances, J also receives some information from the others. Okay?
Also, that's in addition to what
And in the second model, I will assume that J never shifts, completely stays fixed. Okay? So results for the first part, when prominent agents are receiving information. So the notion of learning here will be almost sure convergence to a consensus value, which is equal to the average of the initial beliefs. So why average of the initial beliefs is a relevant quantity? This is essentially capturing our assumption that initially information is dispersed across individuals. So think about each of the beliefs corresponding to some noisy signal about the underlying state, independent. So for a large N, if you just take the average, it will be a good approximation for this underlying state. So essentially that will be our target point to see what happens in the limit and how far is this limit from this initial average. When we don't have any prominent agents in the system, beliefs indeed converge to the 1/n weighted average with the interaction structure I talked about. So that's not too hard to establish, and actually in different contexts, in these averaging problems, gossip dynamics, that has been established in the literature. So what we're going to show is that when we have prominent agents, beliefs still converge to consensus.
That doesn't depend on the network at all. So if some people have high degree and others have low degree, everybody
Connected, as long as you have a connected network.
Everybody contributes the same to the value.
And the reason is that, because this is every link gets activated, and then you and I average. So we take 1/2 average of that, and as on a connected network, that essentially means that everybody will have the same frequency in the limit.
But P is doubly stochastic.
Not necessarily.
So if everybody is only averaging with me, I'm going to have a higher weight.
But then that won't be a strongly connected graph.
Oh, a strongly connected graph is...
So I will give the assumptions, but we're going to induce a graph from P, and that will be a strongly connected graph. Okay? So because of the 1/2 averaging, when you write it down with that P matrix, it turns out to be a doubly stochastic matrix, the interaction over that P matrix, over a strongly connected graph. Okay? So perfect. With prominent agents, we will show that they still converge to consensus almost surely, but this value no longer is a fixed value equal to the average, or not a fixed value at all. It's a random variable. So then the question will be, how far is the mean consensus from that initial average? And that will be our quantification of the extent of social influence in the society. So the next steps will be, can we say something about this difference? And we will provide essentially bounds on this as a function of average influence of prominent agents and properties of the global social network topology. Okay? The first set of bounds will not have the impact of location of the agents, stubborn agents or prominent agents. And then we're going to investigate the effects of location of prominent agents on influence. So we will essentially strengthen our bounds and show the impact of information bottlenecks. Okay. So let me quickly talk about the related literature. There's a vast literature on learning, opinion dynamics. So here I just picked the ones that are most relevant, non-Bayesian ones that are sort of more recent also. So the Groot model, of course, has been used in many contexts. The Marzo-Vajanos-Wibel is a learning or opinion dynamics model which sort of uses this averaging type of rules, gives some limited Bayesian justification to that. The more recent work is by Golub and Jackson. I think Matt presented actually this paper here, if I remember correctly, a few years ago. The idea is they assume beliefs updated using simple averaging rules. If you remember, so every node was taking a convex combination of the beliefs of their neighbors. And the goal of this paper was to provide conditions on the network structure as the network grows bigger and bigger that lead to asymptotic learning. And their performance metric was again similar to ours, average of the initial beliefs. Okay? That was essentially providing some conditions on the network structure as the network grows bigger, which essentially amounts to, in the limit, things become more and more symmetric. But that sort of turns out to be quite restrictive. So what we try to do in this work is to develop a more tractable model, which enables us to write down this difference for a finite size network.
and hopefully bring out what in this network determines how far we're going to be from this metric.
What is not learning? So not learning seems to include two possibilities. We all converge, but to not the average.
Not
or
learning.
We don't converge.
Learning is converging to average. If you converge to different, even to a consensus, but different from the initial average, that's not learning.
It's not learning.
Yeah.
I see.
So in this talk, in both of the models, we're not going to get learning. Or, I will present some conditions under which we are close to learning. But in the first part, essentially, things will converge to consensus. In the second part, we're not going to even have that.
Wait, if they converge to consensus, it's still not learning, though.
No,
That's not
because
the average.
you and I converge to a value, but that's not equal to the underlying state. So misinformation spreads in such a way that we learn something else. Okay?
Yes. Wall Street.
Yeah, exactly. So I also want to point out the relation of the dynamics that we're considering here to some work by Stephen Boyd, Ghosh, Balaji Prabhakar, and Devarat Shah. They have considered these gossip algorithms in the context of distributed information processing. Here we basically, you'll see that the dynamics that we're going to consider is a non-symmetric version of that. Like in their case, for instance, without prominent agents, that's what I was referring in terms of the known result. There's no prominent agent. They do this averaging on a not necessarily symmetric graph, and they converge to the average of the initial values. Okay. Okay. So let me go a little more deeply into the first model. The models will be the same, but the first part, let me call this. So we have a finite society consisting of a set N of agents. Each agent, we're going to assume that will be endowed with some initial belief. We're going to assume that that's a real valued variable. Discrete versions also are possible to consider, which we did in the work with Amin. But here we assume that beliefs are essentially, even if they're discrete, we consider an approximation using a continuum. Time will be continuous. Each agent will be recognized according to some IID Poisson process. And that's really not very, we're not going to use that crucially, that assumption. The only thing that matters for us is that the communication instances will happen according to a Poisson process. Things are independent. And we're going to discretize time according to the meeting instances, because that's when the beliefs change. And xi of k will be the belief of agent I after the kth communication. So let's look at what happens for a particular communication instant. Conditional on being recognized, agent I meets agent J with probability Pij. Okay, that was our P matrix.
This is I has been recognized.
Yeah. Yeah. And because everybody has an IID clock, let's say with 1/m probability I is recognized. Conditional on that, I meets J with Pij. At which point one of these three happens. With some pairwise specific probability beta ij, they agree, exchange information. Both of them update to the average of their current belief. With some specific probability, pairwise specific probability, they don't agree. There's no exchange of information. And with some probability alpha ij, I basically inherits most of J's belief. Here, epsilon is just some positive probability that he may actually keep a little portion of his current belief. So this is epsilon greater than 0. It makes the analysis a little easier. Even when epsilon is equal to 0, what I'm going to say will be valid. So J will be a prominent agent now, more mathematically, if he can influence someone else. Yes?
Is gamma ij going to change the dynamics in non-trivial ways, in the sense that can I just ignore the clock ticks if they correspond to a disagreement?
What do you mean? I mean,
so if they're the same, it's trivial in the sense that I can slow down the speed of the clock.
Yeah.
So I can ignore the ticks. So if they're not the same, I wonder how things change if things are asymmetrical.
It changes the rate, obviously.
Right.
Yeah,
Right.
it
So
changes the rate. But
rate
yeah, but even if they're all zeros, it doesn't change the convergence properties.
Exactly.
Yeah. And I'm not going to talk about the rate. I mean, you can write down the rate, but it's pretty lousy.
So the chain will be non-uniform if gamma ij are not the same for
Yeah.
different ij's.
And if we disagreed, there's a positive probability we would be matched again.
Yes.
And so what's the motivation for that? You and I disagree, and
Maybe today I don't like your opinion, and tomorrow.
tomorrow.
That's a very valid comment. No, that's a very valid comment. This is a non-Bayesian aspect of these models. We keep these parameters fixed throughout the time. It's a very interesting, I think, extension to consider time-varying or even state-dependent changes on these parameters. But this is just assuming that we keep sort of the same mechanism of interaction between individuals. Okay. So evolution of beliefs, how can we write it down? How can we analyze them? So to be able to write them compactly, I use the usual trick. I put them all in a vector, all the beliefs. So x of k is my belief vector. With this belief vector notation, we can now see that the agent beliefs are updated according to the following: linear, time-varying, and stochastic. Actually, random, let me call it, random dynamics. Here, WK is a random matrix given by, with a particular probability, it's the averaging matrix. With this alpha probability, it's the influence matrix. And with the remaining probability, nothing happens matrix. Okay? And the nice feature of this WK is that, that's why I call this random and this stochastic, it's a row stochastic matrix. In the sense, its row sums are all equal to 1. Okay? And that makes analysis sort of tractable, because now we can actually view things in terms of Markov chains and consider their stationary distribution for characterizing the limiting behavior. Okay? And I will mainly be focusing on expected opinions. So the expected value of this WK, or the mean dynamics, would be of interest. And the expected of WK I refer to as W tilde. Since things are IID, this is just a constant matrix. And I refer to that as the mean interaction matrix. Yes?
Just make sure that I got it.
Yes.
So you said it's a row stochastic matrix, but it's not doubly stochastic.
It's
right?
not.
Yeah.
I mean, here it's just the probabilities are all adding to 1, which basically is making
Exactly.
But making it row stochastic.
That's a very good point. Let me actually elaborate on that. So if you write down W tilde, as Jennifer said, in terms of all these probabilities, one can actually notice an interesting decomposition. So this decomposition essentially takes all the A's, this nice averaging parts, and the identity, which is all symmetric, right? These are all the symmetric parts. And the non-symmetric, so we put the non-symmetric part apart. And I can actually call the first part T, the second part D. Okay? So T represents essentially the PIJ, AIJs, these underlying social interactions. When
so it's the egalitarian part.
Exactly, exactly. So we refer to that as the social network matrix. And because of its nice symmetric structure, not coming from P's but coming from AIJs, it actually is a nice doubly stochastic matrix. So it's not only row stochastic, not only rows add up to 1, but also columns add up to 1. It's a symmetric matrix. Okay? And this part is sort of the J, which is the influence matrix, so I refer to that as the influence matrix. So what this essentially tells us is we can get that W tilde and decompose it into a nice doubly stochastic part. Then why do I call it nice? Because we know the limiting behavior of products of such matrices. They actually converge to uniform distributions, which are essentially recover our average of the initial beliefs. So it's this part that's creating the essentially difference from that initial average. And that will be key in the analysis that I'm going to present. In particular, I will view this D as a perturbation on my doubly stochastic part, do a perturbation analysis, and try to see how different I am in terms of the stationary distribution from the initial, from the uniform one.
So PIJs were not symmetric, right? PIJ is not equal to PJI.
No.
Okay. And still you're saying that the first part of this is a symmetric matrix?
Yes.
I see.
We can check that. I'm pretty sure I tried that a lot. It's a symmetric matrix. This is a symmetric matrix, and another thing to notice, and this is something we can check also. I did check it actually this morning. The sum of the rows add up to 0. That will be important because the way I can see this as a perturbation. So I will not change the probability structure here. Yes.
Remind us, please, what is gamma ij?
Gamma ij is this not agreeing probability. So remember, it's disagreement probability.
What was AIJ? AIJ is a matrix.
Where is AIJ?
Green.
Alpha ij is the probability of I influencing j.
No,
but
it
no,
was
it's
an A sub ij.
He's talking about the matrix.
Sorry,
AIJ.
the matrix is the disagreement matrix between I and j.
So that is a symmetric matrix.
Yeah, this is basically in the ij, if you do this, ij entries, 1/2, 1/2, so it has 4 1/2s. Okay, so assumptions, and these are important, I think. So the first one is standard. So we're going to assume that we're going to consider a directed graph N and E. E is the set of directed links induced by positive probabilities, Pij. So think about all ij for which
So
Pij
everybody
is
has to
positive.
kind of live with the consequence of their own, of their own opinion, because it can come back to them. Right?
Exactly. This graph is strongly connected, so information does not get trapped in a subnetwork. If it gets trapped, we don't really hope much in terms of, reaching anything, consensus or anything. Or, if that's the case, we can just analyze them separately. Yeah. So that's okay. I think that's not something I'm too worried about, that's not a very stringent assumption. This is the one that changes everything. What this says is, and it's a bit cryptic the way it's written, for all ij in E, sum of averaging plus influence probability is positive. So what this says is, if you consider some agent I, either he averages with some j, or he is influenced by j.
So in other words, it can't be all the nothing interactions.
Yeah.
Right. It can't be all the. There can't be any pair for which that gamma is everything. That
Yeah. So
happens,
that
and no
I never changes its opinion. So that
Right.
I will always, even if with very small probability, will get some information from the rest.
Right.
Okay. So this is the.
That also, if that didn't happen, it's obvious that how's anything going to converge, right? Because
Exactly.
you're just stuck there.
Exactly.
Right?
Exactly. So this, but in terms of thinking, having some economic intuition, this essentially captures scenarios where we have some, strong entities which receive information
Well,
from.
there's no tea party in your.
In the second part, there will be. Yeah. So essentially, we call this assumption no man is an island assumption, and we will see relaxing it later. So let me talk quickly about the results. I have 1.5 hours, right?
Yeah, with questions, so
Okay.
we can.
I will skip things accordingly. So if there are no prominent agents, this is a standard result that all the opinions converge to the average of the initial. Our result here is basically stating that even with prominent agents, we converge to some consensus belief x bar with probability 1. But now this is a random variable. So each sample path may actually take a different value. But the good thing is they all reach a consensus. All of them will have the same value in the limit. Quick.
The epsilon bigger than 0 here, right? So
Yes.
you
I think it works even without that, to be honest. But the proof, writing the proof for the paper was a little bit shorter with that epsilon positive. Because of this assumption, you can still work with epsilon equal to 0. Because even when epsilon is 0, you still get some information, so you actually enable mixing of everything. So quickly about the proof,
When you say it enters into a random consensus, is random depending on the history or on the initial condition or on what?
It is random. Of course, it's random because the interaction is random. In terms of the initial initial values, it does also depend on the initial values. Because basically, so the idea is, let me go over the proof and then I'll come back to that question. Very quickly, the proof is like this. Recall the way we wrote the dynamics. X of k plus 1 was wk times x of k. So to be able to analyze the behavior of x of k as k goes to infinity, we can essentially think about taking the product of all these wk's. That's what these transition matrices are doing. So essentially relating some value at k to some value at s, let's say s is equal to 0. So the next step is to show that with positive probability, if you think about a large enough window, all the entries of this matrix are strictly positive.
So there are multiple ways of analyzing this kind of dynamics. I just picked this one because essentially one can make a parallel to matrix properties. Think about, for instance, a simpler case where these W's were all deterministic and the same matrix. So this would be just like W to the K minus S. Okay? So this property of having a matrix when you raise to a particular power all entries are positive is exactly the definition of a primitive matrix. So a primitive matrix is one which has a single strictly largest eigenvalue in magnitude and an eigenvector of all positive entries. So because of our row stochasticity, 1 is an eigenvalue with eigenvector 1, 1, 1, 1. So primitiveness essentially says that 1 is the largest eigenvalue in magnitude, rest is strictly less than 1. So we will essentially get a nice convergence property because only one of the eigenvalues essentially.
So you're saying this is all being driven by just
that particular largest eigenvalue.
So between the largest
by the gap of the, but that's just coming from your row stochasticity.
Row stochasticity plus this.
Plus that. And
plus
strongly
that.
connected.
I'm
Good.
essentially giving the intuition
fine. So
for a
that's the
simpler
gap.
case.
So, right.
And this is essentially establishing a property similar to that. And
so
then
you're getting something about the rate then.
We can write it down.
Yeah.
But I say it's lousy because we don't have doubly stochasticity. It's pretty, actually we wrote it down in some version of the paper, but then we took it out because it wasn't very...
You could get sort of exponentially small gap between the first and the second.
Yes, yes.
But basically that's why we go to this path, establish this property, and then pick this natural Lyapunov function in terms of looking at the maximum opinion values minus min, and shows that it decreases with positive probability. Okay? And I was going to come to your question.
You wanted to know is it random depending on where you start, or also does it depend on the path?
Yeah, it depends basically on the path as well as where you start, because this establishes that this matrix converges to a particular matrix which is not rank 1, and times x of 0 is your limiting value for x. So it depends on both of those factors. Okay. Perfect. So now that we have convergence to x bar, essentially I'm interested in providing an upper bound on the expected value of the difference between x bar and the initial average. X bar, especially since we're interested in expected x bar, that's essentially the dynamics that is governed by this W tilde, expected WK. So under the assumptions that I mentioned, you can view this as a transition matrix of an irreducible aperiodic Markov chain. Immediate implication, we have a stationary distribution pi. And moreover, expected value of x bar is actually a convex combination of the initial averages where the weights are given by this pi. Okay? So the whole thing essentially boils down to what is this pi? Or how does that pi relate to the underlying network? Okay? So essentially, to recap, this is what we're interested in. Pi I'm going to be referring to as the consensus distribution. And pi I minus 1 over n is exactly the excess influence of agent I. So the first result basically provides a bound on this difference, pi minus the uniform distribution. And the bound is in terms of this Pij alpha ij over n, which is the average influence of the agents. Remember, alpha was the influence probability. Pij is half, but the rate at which that ij is activated. So that's the average influence. And delta is a parameter which I wrote down here explicitly, but it doesn't really mean anything looking at it like this. I will present next another result which actually relates it to the mixing time of the graph. But for now, this was maybe done to write things more explicitly in terms of the graph structure. Delta is actually related to the maximum shortest path length in the graph, which is d, as well as the minimum values of these Pijs and gamma ijs. Okay? Let me, before going into the mixing time.
This is not, we're not describing right now the mixing process, but what the stationary is.
Yes.
And I see. But somehow the mixing constants influence what the stationary vector is going to be.
Exactly. I'll show you why in a second. So that's, I think, embedded in the proof. The proof actually uses a, I think, a very nice and simple result from Schweitzer. This is actually MIT PhD thesis from the math department that we found in the library. So the idea is basically use the perturbation theory of Markov chains. So this is basically what this result says is if you have an irreducible aperiodic Markov chain, transition probability matrix T, stationary distribution pi, consider its fundamental matrix defined this way. T infinity here is the matrix of stationary distributions. So all the rows are pi. You can show that y is given by this sum here, t to the k minus t infinity. And what Schweitzer's result says is, if you think about the perturbation d on t, and this is a perturbation with row sums all equal to 0. So we're thinking a new transition matrix t hat, which is t plus d, and let's assume that it's still irreducible and aperiodic. Okay? And what this result says is that the perturbed Markov chain has a unique stationary distribution, and it characterizes the difference between pi hat and pi in terms of the d perturbation and the fundamental matrix of the original Markov chain. Okay? So it's basically this result that I will be using, pi dy times I minus dy inverse. So in terms of our problem, what I will do is I'll consider t. I use the same notation intentionally. T will be exactly our starting point. I know it's pi. That's a uniform distribution. So basically, I will characterize this. I know the d. That will be the influence part. So let's try to see what this little d is. So that's what it says here. So I try to obtain a bound on this dy, the matrix norm of dy.
T was the nice doubly stochastic part. This was roughly what happens in fair exchanges. And D was the part where the prominent
influence,
the influential pairs play. Okay.
So dy, let me also go back. Now what, oh sorry, go. So dy is, so I'm trying to characterize this d or the norm of this dy here. So I consider an induced matrix norm here. By definition, this is dt to the k minus t infinity. T infinity in my case is all ones. Okay? So if you multiply that with this d matrix with row sum equal to 0, that disappears. So I end up with dt to the k. So Madhu, I think your question is coming here. Now, as you see, the difference is driven by how we're actually converging to the stationary distribution.
Convergence of t determines the eigenvalues of w hat.
Exactly. So from here, we use the special structure a little more, you know, what this D matrix does, T to the K does. And if you actually write it down, I'm going to skip a few steps. Essentially, you can essentially boil down the problem into, you know, looking into this difference, max minus min, where you're considering some linear dynamics driven by T. And you can show that it decreases geometrically at this rate delta and then get your result. So you can also provide a bound on the L2 norm, and this is much more, I think, intuitive. So in this case, you can write it in terms of the average influence and lambda 2, which is the second largest eigenvalue of the social network matrix. This is probably tighter than what I just talked about, because I think what we did explicitly was trying to bound this lambda 2 in terms of these path lengths and so on. Although that's my intuition, so I'm not making a formal comparison. But this is basically, I think, easier to study the difference between these two. So what does this imply? This implies that if you have a communication graph with small lambda 2, essentially fast averaging, small lambda 2, large spectral gap, small value of the bound, so you will essentially get that the extent of influence is more limited. Okay, so if you have fast mixing graphs, then influence will not spread too much.
This is, no matter what, this is not promising learning at all by our definition, because they're not converging to the. You're going to converge to pi, but pi is far from.
You can. I mean, now I'll show you a few examples. I mean, we can show some. We can put some conditions under which this goes to 0.
Oh, this is 0, right? Because there is no, I mean, this is not a function of t on the left or the right.
It's a function of t. Lambda 2
the
is
faster the mixing, the closer you are to the learning, right?
Yeah.
So the closer you are to the
closer,
learning.
but you're always going to remain an absolute distance far, independent
Why?
of how long the time goes.
Why? I mean, if you have this part going to 0.
Where is t? But that part is independent of t, isn't it? Little t, it's independent of time, isn't it?
It is independent of time, but what this says is basically in the limit, depending on this right-hand quantity, you may actually converge to learning.
So limit of over what quantity? I mean,
This is all about in the limit as k goes to infinity. Consensus in terms of we reach a consensus in the limit, and pi is our consensus
right,
distribution.
I don't see k as anywhere in the right hand side.
But it's not in the left hand side either. So why do you expect to see k?
So how do we converge as a function of k? How can you take a limit over k of a constant? It's a constant.
I'm not, okay, let me put it.
So maybe if you want learning, one of these parameters should go to 0.
So I will actually, maybe to take this to 0.
The right hand side, if it's 0, I understand that it can converge. But if it's anything other than 0, it seems like not learning by definition.
Yes.
Okay, good.
Yes, and this is basically what you can put some conditions on the network. Let's say, you can think about larger and larger graphs. As n goes to infinity, you can make this right-hand side.
As n goes to infinity,
yes.
I can imagine that there is some function which goes to 0.
But if you're keeping the right-hand side fixed, with k, you're not changing anything. You don't get learning.
Right, okay. Good. Okay. So it's not clear to me what's the definition of learning where the size of the network is going to infinity. Then it wasn't clear whether it was a function of the size of the network going to infinity or the size of the number of clicks going to infinity.
So learning is defined for a fixed network.
For a fixed network?
Yes.
Okay.
For a fixed network of size n.
And it's learning, and you can learn if this left-hand side quantity is 0.
Yes.
Okay.
Yes, and what I'm saying is what I mean, just repeat, essentially I'm repeating, I mean, for fast mixing graphs, you will be closer to learning. Okay. Perfect, but now I think there's an issue with that, what I said, right? Because if the graph is fast mixing, wouldn't you expect influence to spread faster so that actually learning is worse, right? But this is basically coming from our earlier assumption that even the influential agents get some information. Because of that, basically, beliefs of the prominent agents will be moderated by the society before they can infiltrate it to the whole society. So that's why it's not really a contradiction in terms of what we see from this bound. Okay? So it's very much driven by that assumption.
And the lambda 2 is lambda 2 of the social network, right?
Yes.
It's lambda 2
yes.
of the
T.
Yeah.
Not of the whole thing.
No.
But D doesn't matter? Like any property of D doesn't quite matter in a bound?
Well, it's a bound, right? It should matter. So that's my next point here.
Because that condition in the bound doesn't.
Yes, exactly. This is a loose bound in some cases because it doesn't depend on the location of the prominent agents, right? So let me quickly, I mean, these are things probably just as a repetition for a lot of people, but let me try to understand the bound in terms of some more explicit properties, and let me capture that through the conductance of a graph. So let me think about only the t part, nice part of the graph, and define an undirected graph which is weighted with this t matrix. So thinking about this as the t-induced graph. The conductance of this graph is just the normalized min cut. So we think about all the cuts, sum the values of these t's over the cut, divided by the smaller portion of the network. So for a complete graph, if you actually do the calculation, the conductance turns out to be scaling. I'm dropping a lot of the constants here, but it scales as a constant. Okay, and so we gave our bound in terms of the spectral gap. We can now relate it to the conductance using the Cheeger's type inequality. And what this says, for instance, if we try to understand what's going on for complete graphs or expanders. These are cases where spectral graph is uniformly bounded away from 0. And if you think about locally prominent agents, namely this quantity scales as a constant. So we're thinking about agents with just
influences a constant portion of the society. And the number of local prominent agents are constant, or they grow slower than n. Okay, I'm trying to basically make sense of this bound. What I'm saying is that this part goes to 0, lambda 2 is bounded away from 1, so this part is a constant. So in that case, we can actually expect that for large n, this is close to expected of x bar. Okay. So that says in a connected society, if you have large connected society, misinformation or influence will not spread a lot. And the more connected the network, the less the effect of locally prominent agents. So let's sort of elaborate more on that. As I mentioned, this does not depend on the location of the prominent agents. You can think about another graph. This is basically the barbell, which is a commonly used social network model. And let's think about one forceful edge here. I influences j, and the rest is just regular. If you look at here, intuitively, influence here also should be limited, because especially around this forceful link, things are locally very well connected. Okay? But if you look at this conductance of the barbell graph, this is basically scaled as 1 over n, and our previous bound basically gives us a very large value. And the issue seems to be here, we're not really looking at the right cuts. I mean, it's not the minimum cut of the entire graph, but it's really the cuts associated with the forceful edges. And that's essentially this information bottleneck idea. We can actually provide bounds in terms of relative min cuts. And by that, I mean only the cuts that separate the prominent agent from the influenced agent. And we can actually write down a similar bound in terms of that. Okay? So essentially, what these bounds enable us is, instead of computing this exactly, which can be, you can actually, in the paper we give exact characterizations as well, we would like to get some idea of some macro properties or some parameters of the network, which we can use and identify which networks are more robust to spread of influence or misinformation. So that essentially concludes what I want to say about the first part of the talk. So let me now focus on this no man is an island assumption. This was the assumption that Christian was talking about in the beginning. So it's a good approximation when essentially prominent agents are influenced by others, but not a good assumption when you're thinking about extremist groups coming to the party. Without no man is an island, of course, there's no almost sure convergence to consensus. But what can we say about the limiting behavior of opinions in this case? Because this is basically, especially in these contexts, a situation that we encounter a lot. A lot of the opinion dynamic models or learning models work with consensus in the limit. And that's not what we see in a lot of the societies. We see fluctuations. So the goal of this work was to see if we can characterize fluctuations, not the consensus value, again as a function of the network.
I mean, sort of in the previous result that we just saw, if everybody is sort of very opinionated, this should imply that you shouldn't really be getting close to learning at all, because everybody is sort of relatively stubborn. And so what aspect of that result sort of captures the fact that you would be far from learning? So there was the T and the D, and it looked like no matter what, you should be converging closely. It wasn't a function of who was very
but wouldn't it take a long time in that case? I mean, wouldn't that show up in the rate which you didn't give to us? If there's all this unequal stuff, it kind of bounce back and forth a lot. I would think. I don't know.
It's probably it would show up in the rate.
That the D matrix is sort of large. It's a large perturbation, or where would it show up in that? I mean, one would sense that if everybody is sort of insisting on their opinions to everybody else who speaks to them.
So you're essentially considering a scenario where all these alpha ij's are positive. So you have this D matrix will be
Right.
These will be large. But because, as I said, of my assumption of no man is an island, fine. We will sort of be bouncing back and forth, but in the long run, we will converge to a
So you would have
limit.
seen that in a rate which she wasn't giving us.
Yes.
But somehow.
But it's not going to affect what you converge to, see. So
No, it may.
It will.
Converge.
It will, of course. I mean, I presented these bounds in terms of these alpha ij's, as well as where these agents are located. If they're located at the central part, of course, it will change that right-hand side of the bound. Okay.
But so in this one, okay, so this will essentially, here what we're going to show is that we're not going to converge to a consensus, but the opinions actually converges in distribution to a non-degenerate random variable. Okay, so the non-degeneracy is important here. That means, you know, things will keep oscillating.
So can I rephrase your, so there's sort of this well-known thing that people say Bayesian agents can't agree to disagree. And you're saying even opinionated agents can't agree to disagree. They will eventually agree, unless they're sort of really stubborn.
I think these are very different models. So
I always thought it's really an idea of the Bayesian learning that you can't agree to disagree, whereas you show that actually more general you can come up with models where we still can't agree to disagree. In the end, we'll agree to your model.
It makes sense, right, Christian? There is, if you say that, you know, I need to execute the Bayesian or the averaging step for, you know, t sequences in a row, the probability that it happens is epsilon to the t, which is positive.
Mm-hmm.
So in the limit, you will find sort of t hits where you all agree to agree.
I think this is a very simpler version of that because of that epsilon, or, you know, that positive probability that we've introduced. Then there's no way you can disagree. But that's very much driven because of that particular assumption. So.
But you said you thought the previous one would go through just with the alpha plus beta positive for every I in J.
Yes, yes. So that's I didn't mean epsilon in that sense. I meant alpha plus beta positive probability.
Good,
Yeah.
good.
Sorry.
Good. Okay.
Yes, Kwang, you had a
So
question.
in this case, alpha plus beta would be 0 for some.
So this will be a slightly different model. I'll just talk about it in a second. But the key idea, so it will be a slight generalization of the previous model, although I think the main ingredients are the same. Here, the only main component is that stubborn agents never change opinion. Okay, and so you can think about it as if there were an alpha, that would be a 0.
So they feed into the network.
They just keep putting information to the network. They never change themselves. So the contribution here is to essentially provide explicit, to show that, well, we converge in distribution, so we can talk about some well-defined limits in this case, and we will characterize the mean and correlations in terms of the network properties. So the model is very similar to before, except that this set S is now stubborn. So we start from some connected network, NE. Let's say it's undirected, although, you know, the paper essentially starts with a directed version. This is slightly easier to state some of the results. Beliefs are, again, continuous variables. Our set of agents is now A union S. S is the stubborn agents. They never change opinion. Regular agents change opinion. Before, I was essentially assuming they just take averages, for instance. Here, this is a slight generalization, well, two generalizations, essentially. One is I will consider things in continuous time. So basically, I will consider now edges sort of activating according to a Poisson process with rate RAV. And whenever A is activated, A updates his opinion to a convex combination of XA and XV with some theta AV trust parameter. So it captures essentially how much A trusts in me, and that's also fixed in time. Okay. So typical sample path behavior as we expect, right? The blues are stubborn agent of one type, reds are of type 1, the other one is type 0, so these are, they never change opinions, and the regular agents keep on oscillating like crazy in the middle. And one can show formally that actually beliefs of each regular agent keeps on oscillating with probability 1. They never converge. And two distinct regular agents that are actually connected to two different stubborn agents, there will always be persistent disagreement between them. Okay? But one interesting thing actually to notice from even this example is if you think about sample averages, they have this nice smooth behavior. So there's no convergence to a common value, but each of them actually seems to have a limit. Actually, this is something one can show, that probability that Zi of t converges is equal to 1. So before I present the main result, so this sort of will be like, seems like Xi of t is an ergodic process, and these sample averages, or, you know,
or the means do converge to a particular value. Okay, so let me look at a special case. This is basically a realization that came a little later, but if you think about the case when theta AV is equal to 1, what happens? When theta AV is equal to 1, when this edge gets activated, A goes and picks up V's opinion. So that's actually the famous water model without the stubborn agents. So it's been used, I think, not only as a simple model for opinion dynamics, but of course diffusion of technologies, innovation, epidemics, and so on. And the main tool here, don't know how much I should talk about this to this audience, but it's basically the dual process, which enables one to trace back the sources of the opinion. So if you're thinking about, for instance, let's pick an example, this node, let's say agent A, and you want to figure out where xa of t at time t comes from, you look at its last meeting instance, let's say with agent V. So xa of t is xv of t minus u1. Okay? So, and then you can repeat this, and that induces basically a random walk V, which starts VA, I'm sorry, so because we started it at A, so VA of 0 is A, it jumps to V, jumps to W, and so on with the same rate as the original process. So if you read, that's one process. If you're interested in tracing the opinion of all of these agents at time t, you can start a similar process at each of these points, run them backward in time, and then these processes are such that either they basically meet at some point. Whenever they meet for the first time, they stick together, right? Because from that point backward, their history is the same. Or they hit the set S, which is the stubborn agent set, and then they will stay there, no more changes after that. So this is basically a coalescing random walk with absorbing set. And this gives basically a nice way of viewing this opinion dynamics process. It has the same distribution as this XVI, VI being the dual process itself. So this immediately tells us from here, or from the known results about, well, one has to add the stubborn agents. So VI, this is a finite state random walk. VI with probability 1 converges, or will hit the absorbing set, right, with probability 1, meaning VIT will converge in distribution. This has the same distribution, so XIT will converge in distribution. So for this special case, we can see that the opinion process converges in distribution.
Right, but if the betas are not 1, then they don't coalesce.
Exactly, exactly. So that was just the special case to give us some insight. This is actually a very different proof. This to show that when thetas are not 1, one can actually show that for any value of the agent beliefs, the agent belief vector converges in distribution. And here the initial values, okay, let me hold on to what I will say for a second. This is just saying that for every value of stubborn agent beliefs, we converge in distribution in the sense that if you look at the expected value of phi of x of t for any bounded continuous test function, you get converged to some expected of phi of x. We call this x as the ergodic belief of agent I. And what this says is basically take phi to be identity, expected of x of t goes to expected of x, second moment goes to expected of x squared. So we can, even though things fluctuate in the limit, we can at least talk about some well-defined moments in the limit. Okay? So let me next talk about how do we characterize these ergodic beliefs. And ergodic belief, remember, was the random variable, non-degenerate random variable that we were converging to. So to characterize those beliefs, we consider a random walk on this N set of agents with state transition rate matrix. HAV is theta times R, activation times trust, and diagonals, of course, minus of the sum. We denote T as the hitting time of the random walk to the set of stubborn agents. Okay, this is basically the first time that the random walk hits stubborn agent set S. And let me
It's a stubborn agent, then it's
and then let me define a hitting probability distribution gamma I over the set of agents, which is gamma Si is the probability that V hits the stubborn agent S at little s. Okay, so few things to notice here. This is a conditional measure I, meaning given that V of t starts at I. Okay, and that's why we have a parameterized distribution here. And what this essentially is it's sort of from the perspective of I, characterizes the relative importance of a particular stubborn agent S within the stubborn agent set, capital S. Okay, so we have a few characterizations in the paper. I picked two.
Can you say something about then, like the basin of attraction of the different stubborn agents or something? If you view the process. Okay. Yeah.
Exactly, but I think it's it. So the first characterization provides an expression for the expected value of xi in terms of basically the values of stubborn agents. And here, this gamma s is a probability distribution. So what this is a convex combination of xs, where the weights are exactly these gamma si's. Okay? So this relative importance of this particular agent I from I's perspective. Okay? So this is nice. It's a very similar characterization as in previous case, expected limiting opinion is convex combination of initial beliefs. But one thing to notice here, I think, especially when you're thinking about this learning notion, there is no learning notion here, because the initial opinions of regular agents have no impact. There's no xi of 0 here. It's only about excesses, and that's also expected from this model, because you start with some initial values, everything else gets wiped out, you just sort of get pulled between these different values of these extremist groups. I forget everything else, I guess. That's the transition rate matrix, the way I defined it here. So because essentially the way to prove it is you take this random walk, you write the evolution, and you look at the way the opinions evolve, and you show that basically, yeah, exactly. And that's this. So that's essentially useful, I think, as an interpretation of what the limiting values look like. And what this gives is essentially, it's actually the unique vector satisfying this system of linear equations with boundary conditions. Special case. If you think about basically these rates being proportional to the degrees, the way each of the links are activated, and let's assume simple case, theta AVs are all equal to theta, then this actually can be written as this form. So that gives you a nice linear system for evaluating what the expected values will look like in the limit. Okay, so this can actually, this is helpful. We can get any graph, hopefully not too large, and be able to compute these expected values. We did that for 2 cases, 3, well, a few cases, but I'll show you the 2 cases. 3s, it's particularly simple. In this case, if you think about, for instance, let's think about the simplest tree line with 2 extreme agents at the end with values x0 and x1. It's just a convex combination proportional to the relative distance between one agent versus the other. I didn't talk about the variance, but you can also compute it. It's a quadratic, being maximal for the middle nodes, which are the central nodes, because these are the nodes exactly which are pulled back and forth between the two. And for such trees, for these agents which are just connected to S0, of course they will adopt this. But for those who are sort of affected by both, it's essentially this gray color scale, which essentially depends on the relative distance. Barbell is also interesting. If you do the computation, you get basically something. This is not very interesting. It essentially says that all of these have the same value, which is close to S0. All of them, these are slightly different because they get influence from the other side. But if you're taking n to infinity, you see that things polarize between the two. So essentially, for such graph structures, we get complete polarization around the 2 different opinions. So the next step is fine. This gives us a way to compute expected values. I'm almost, I think, I have another part, but I'll be quick about that. But it's essentially for large graphs, especially for complex and large graphs. Maybe you can do it computationally, but it doesn't give you much insight about when you're going to have polarization or dispersion of these ergodic beliefs. So the next step is to provide a bound on the ergodic belief differences, how different expected xi is from one agent to the other agent in terms of some network properties. And this parameter turns out to be relevant. I focused on a special case for simplicity. The paper has the more general case, but it's a bit more not that easy to explain. I think it contains some measures like pi of s, which is not, it's in terms of this pi of s, whereas in this case you can write down what it is. So this is in terms of, let me first start with the simpler terms. D star is the minimum degree. D bar is the average degree. Tau is the mixing time. Okay? And pi s here is the invariant measure of the stubborn agent set, which in this particular case is nothing but the fraction of edges incident to the stubborn agent set to the rest of the total number of edges. Okay? Or in other words, it's the relative size of the boundary of the stubborn agent set. Okay? How much they are essentially influencing the rest. And the bound is actually simple. There exists some psi and sigma such that the fraction of agents whose expected belief is different from some particular psi. I don't know what it is. I'm just looking at the dispersion. It's different from psi by some epsilon is bounded from above by some constant divided by phi. Okay? So forget about what this constant is. It depends on epsilon and other things. But what this says is if you define a society as highly fluid, as one in which as n goes to infinity, phi goes to infinity, then in those societies we have that expected values and variances concentrate. Okay? And let's think about why that's the case, or let me try to give as best as I can the intuition. So this going to infinity is tau times pi of s going to 0. So mixing time is fast. Pi of s is small. So this is basically a graph in which mixing time is fast, pi of s is small. So stubborn agents have approximately equal influence on the rest of the agents, with the caveat that only in terms of the first and second moments. Okay? So in terms of the general distribution, this is not saying.
Is it because somehow this is not capturing, I mean, like the tau is not capturing how the other moments would be acting, or why is it?
Well, this is just what we're providing. We haven't looked at others.
Okay.
I mean,
so you're just looking at the variance.
Yeah.
Sure. Okay.
Mm-hmm. Okay, so this is basically what I want to say, but I'd like, as I said, there's a broader research agenda behind all this analysis, and that's actually, I just want to sort of mention this paper we have basically on, that also talks about optimal network modifications. This is a sort of slightly different model, but it's essentially discrete opinion model. It's a water model, and what we considered there is actually characterizing expected values, variances. There are interesting characterizations, but there's one part which I want to focus on, which is the optimal stubborn agent placement problem. And that question is basically, suppose you have agents of type 0, let's say 2 types of agents. You would like to choose k nodes among the regular agents, turn them into type 1, such that you have the maximum influence in the limit, at least in the expected sense. Okay?
Kind of viral marketing with
exactly.
stubborn, with absolutely single-minded people.
Exactly, but it's a different setup. It's a different metric.
Right.
It's a different setup, and it's actually people have been very interested in this, especially in the context of conflict situations. So if you have some extremist group in the network and you're essentially trying to influence opinions and you have limited number of agents that you can target, which nodes should you target, at least with respect to this metric. And you can write this, formulate this, of course, as a mixed integer nonlinear program, but what we showed is basically that we can solve it explicitly for k equals to 1 and k greater than or equal to 2. We use the usual trick. Things are submodular, so we have some nice the greedy algorithm actually has some nice performance guarantee. So how am I doing with time?
I mean, how long do you need?
I'm just going to show a few examples of, that was fine. That gave us a computational way to find these agents, but we wanted to understand also maybe some simple examples that give us insight about how to place these agents. So those are the few simple examples. So this shows us if you have a single 0 agent, how are you going to place the 1 agent? And different shadings are essentially different examples. So if you have a 0 here, then essentially you try to place it as close as possible so that you have dominance over a larger portion of the society.
Kind of blocking.
Exactly. You try to create a bottleneck with the rest. So, okay, let's build on. If you have 2 zero agents, again, similar situation. This one, maybe the first guess is somewhere in the middle, right? But if you do it in the middle here, but then, it seems like a larger piece is still dominated by 0, so you try to pull it back as much as possible without losing a lot of the things to them. So it's fun to play with these things, I guess, to get some insight. So barbell graphs, if you have a single 0, you note that these are complete, but this one is not, right? Yeah, this one is not. So you place a 1 here. If you have zeros here, then again, it's not. Yeah, I mean, my first guess would be somewhere here at the center of mass, but then actually it turns out that being equidistant to both is sufficient, so you try to pull it back as much as possible so you get the line. And another example on barbells, this is basically one in which P1 is, because the first intuition was I always place it here. That's not necessarily the case. If P1 is much larger, you can actually try to place it inside also. Okay, and finally, one more example.
So could you have a center of influence, some metric where you say, okay, well, this is from your previous theorems. Is there like a center? It's not the center of mass, but is there something which is the center of influence?
That's a very good point. I think yes, and that should relate to.
You might be able to read that in your proof somehow.
But I think intuitively it will be something like if I place it here, it will essentially be 2 stubborn agents, and it will be about which one am I going to be absorbed by first, or some metric defined through that. Okay, final example, and this is actually, I had a student who worked on the Afghan society. This is a network generator model that he built, which is supposed to represent that. So he actually used some synthetic data as well as some notes from political science to try to understand the structure of the Afghan society to actually create a network generator model. So this is not real data, that's what I mean. And this is basically, and no wonder I put T as your one of the extremist groups. What?
I'm kidding.
Anyway, so there are 3 type 0 agents, and the question is where do you put your type 1 locations? So it turns out that the sequence.
Who's recording this work?
I have nothing.
I was thinking.
It's yeah. Anyway, so this is just showing that a greedy algorithm finds the optimal in each of these cases. So just to conclude, we presented 2 models of opinion formation. First part was, prominent agents part of the society. We get converges.
Can you ask a different question, namely, what if you could kill one of the opinionated guys, which one you should kill?
We don't ask such questions. We view them as nodes.
Neutralize.
Neutralize, yeah. Well, okay. So it was interesting to observe different kinds of limiting behavior and also try to understand or provide explicit characterization for these. This is an interesting topic, like how do you modify the network to limit influence. So there are, I think, many future directions. If you're thinking about sort of opinion dynamics models in the presence of prominent agents, I put just a few. The first one is what Rakesh mentioned, sort of, I think it would be very interesting to think about dynamically evolving interactions and dynamically evolving graphs. In all of the things that I said, the graph structure was fixed. So actually, we may ask similar questions in that context. If the graph structure changes for whatever reason, how do we analyze the opinion dynamics? And they asked me that question, actually. I'm like, okay. And the second one is also think about strategic decisions in this context. So we're thinking about a game at multiple scales. Now there's the opinion dynamics, but there's a game played among multiple agents in terms of how one can change the network structure or other interventions to change the limiting behavior of the dynamics. So that concludes the talk. Thank you.
So in terms of this dynamically evolving graphs, I don't know if you're familiar with this Chazel's, Bernard Chazel has these results on a sort of what he calls these natural algorithms. There's a very powerful result out there which says that you can have a sequence of graphs varying arbitrarily, which will lead to some form of a consensus at the end. I mean, where every time a node picks a new collection of neighbors, sort of takes their average of their opinions with some, and with lots of perturbation allowed, it will still converge. So it's a pretty...
Then I know the sets of results, especially in the context of this distributed information processing. The assumptions there is that the underlying graph is time varying. And there is some assumptions, mild assumptions though, like either they put deterministic assumptions like over a window. If you think about the joint graph, which is the union of all the graphs, they must be connected.
No? That's Nancy Lynch's work that you're describing.
Johnson 6.
And maybe
but he's talking about the flocking.
Yeah, that's what I'm talking about.
He was motivated by bird flocks and then
exactly.
That's
what I'm also talking about, but maybe different communities.
Maybe okay. I would have to.
But this is also similar. One can actually view this, but. Because of, I think, if you think about the opinion dynamics model, that will involve some of the links being killed, and the assumptions of those, which says over windows things are connected, may not hold in this case. So consensus may not hold. We may actually think about partitions. So that's what I mean. You otherwise.
Which reminds me, he doesn't claim that you will achieve consensus. You'll achieve consensus in the connected components or something.
Okay.
Right.
Okay. Perfect. So maybe I should. I don't know that particular reference. The rest of the flocking literature does address similar questions, but I think under some assumptions which are not realistic for this setup. Okay. Thank you.